Hello students, today we will implement flip-flops, that is RS flip-flop, D flip-flop, JK flip-flop. So I have already implemented the circuit. Okay, SR flip-flop I have designed using 4 NAND gates and associated circuitry, clock, switch, input switches and output LEDs. We can find all the components by clicking plus sign. You can see under flip-flop section there are various blocks. So these are SR flip-flop, JK flip-flop, D flip-flop and T flip-flop. So as far as concerned about flip-flops, these are the building blocks of sequential circuits, right? These are latches and flip-flops. By using latches and flip-flops we can build the sequential circuits. So the major difference between latch and flip-flop is that latch does not have a clock signal, while the flip-flop always works with a clock. Okay, you can see from the circuit diagram I have used 1 kilohertz clock with JK flip-flop, D flip-flop and SR flip-flop. So in a latch, this is a bistable circuit whose output, or we can say next state, depends upon inputs. Basically you can call them set or reset entities. But present state of flip-flop is a synchronous circuit in which the output changes state only when a input trigger is there, input clock signal is there. So only then the output changes its state in synchronization with the clock signal. So for triggering we can use positive edge triggering, negative edge triggering and level triggering. So you will learn these in your theory section. What is positive edge triggering, okay, what is negative edge triggering and what is level triggering, right? So here I have already made the circuit and we can just verify the truth tables. Truth table I have shared file in the WhatsApp group, you can see. So here the connection is set for D flip-flop. So for D flip-flop you can check the truth table. Clock is there, input T is there and output, two output states Q and Q bar, right? So we will just simulate the circuit. I have made connection. Okay, I have taken two LEDs, green LEDs Q and Q bar. Okay, so previously I have showed you how you can add text. Okay, so you can label them as Q and Q bar. So we need to simulate this circuit or D flip-flop. So you can clearly see when there is a clock your Q bar is high, and when I input 1 at D, the state changes with the clock. Okay. Now at input 1, Q is high, output is there. When I switches the input, then again the state changes with the clock signal. Okay. So truth table is verified for D flip-flop. This circuit has two stable states, 0 and 1, right? For one input, output is present there at Q, and for input 0, Q bar is high, means 0 at Q. Okay, so this has two stable states. Similarly, we can verify the truth table of JK flip-flop. We need to stop the simulation, and after that we need to make the necessary connections. Q bar, we have to connect it here. Okay, click on Q, after that click on the LED. So now we will simulate the circuit for JK flip-flop. So you can observe the clock, 1k hertz, 1 hertz clock is there, and when the both inputs are 0 0, no change is there. When J is high, stable state Q is there. If I made J 0, you can see I have made J 0, but Q is still high. Okay, input is stored. Now when the K input is high, you can see Q bar is high, your reset state. This is again a stable state. If I made K 0, you can see this is in reset position. So both the states are stable. Okay, whether it is 1 or whether it is 0. So what will happen for 1 1? It must be a toggle state. Okay, according to truth table. Let me check. When J is 1, K is 1, you can clearly see for every clock signal, your output Q and Q bar is changing. This is toggling. Okay, for one clock signal, your Q bar goes high. For other, your Q goes high. One time Q will be high, for next clock Q bar will be high. So this is just like a toggle for every clock signal. Okay, so hence the truth table for your JK flip flop is verified. So now we will stop the simulation and make the necessary connections for your SR flip flop. For SR flip flop, you can see there is a inbuilt block in this app. I have used that also, and I have made a separate circuit using 4 NAND gates. This is also a SR flip flop. So we can verify the truth table with both the circuits. So let me first try this one. So connect Q to Q and your Q bar to your other LED. So now simulate this. So this is your reset state initially. But once I made S1, you can see your Q is set. This is your set state, and I made S0, but the state is stable. Okay, for 0 and 1 it is stable. Your Q is always high, and it will only change for when I made R input high, but it is again a stable state. Okay, this is a reset state condition for your R1 and S0. According to truth table, this is a reset state, but this is a stable. If I made it 0, then it will show you like this. Your QR is high. So both the states are stable. And your last one, that is uh, 1 1, you can say this is a invalid state, you know. Neither state is stable. This is changing, and very rapidly this is changing. So this is invalid. No storage during this when both the inputs are 1 1. So one thing more, 0 0, we call it a race state. A race state means your previous condition will be there. If not like that, for every 0 0 your Q will be high. One time it can be a Q which is high for 0 0, and another time you will find that for 0 0 input your Q bar may be high. So this is a race state, right? Now you can see your Q bar is high. So this is a race state. Any condition can prevail. So at last we will go through the circuit SR flip flop made by using 4 NAND gates. So just made the necessary connections. And simulate the circuit. Yeah, I have added a clock, external clock, 1 hertz. You can see the output fed back to the NAND gate. It is just toggling very fast, very rapidly. No state is stable during this. Okay, this is a race condition as I told earlier. And for S1 and R0, this is a set condition. Okay, your Q is 1 and Q bar is 0. So you can clearly observe the circuit when there is a clock. Okay, so it is completely depending upon the clock condition, whether it will store the state or not, right? Just observe the NAND gate just next to S switch. You can see a red indication there, that is presence of your clock. When clock is there, output of the first NAND gate is high, and simultaneously this is the input to the next NAND gate. Other input to that NAND gate is 0. So this is hardly making any change to the output, because output is high irrespective of the input. Okay, this is your set state. This is completely depending upon the clock signal. You can observe the NAND gate next to R switch. Output is always high because one of the input is 0. So for NAND gate, if one of the input is 0, output always is high, and this is making both the input to the fourth NAND gate high, which means Q bar will be always low. The LED Q bar will always low. This is your set condition. So again, you can, this hardly makes any change. You can check the outputs of the third and fourth NAND gate. This hardly makes any change. That's why QR is a stable state. Output is always similar. So this is the inner circuit behind your SR flip-flop. Gates are used to implement the design. So this is your reset condition. For reset condition, your fourth NAND gate is always high. Always high input is there, irrespective of the input change. Irrespective of the input change, it is high. Okay. And this is your invalid condition. You can check third and fourth gate output is changing rapidly. So this is a invalid state. Okay, so there must be two stable states, but none of the state is stable, so we call it invalid state. So hence the truth table for our flip-flops, which are the storage devices used in digital circuitry, is verified. So that is the end of your flip-flops: RS flip-flop, D flip-flop, and JK flip-flops. Other one, T flip-flop, is also present in this app. You can practice and see the truth table. So that's all for now. Thank you.